Greetings, the Astro 30 here yet again, and welcome to part 3 of this loudspeaker protector slash power supply for an amplifier project, part 3. I think I said part 3 twice. Anyway, welcome to part 3. Now, first off, you may be asking yourselves, how come we're still looking at a breadboard? How come I haven't, moved on to the PCB design stage yet? Well, as I stated previously, when designing a circuit or even modifying a known working design to your own tastes, you always put it on breadboard first, or some form of prototyping before you actually go and commit to a real printed circuit board, proper printed circuit board, whatever you want to say. Because there's nothing worse than you build it up in the final stage on a proper PCB and find things blow up and components fry or whatever because there's something wrong with the design. Now, another reason is you've got the preliminary design done. Okay, can we actually refine that design? Can we make it work a little bit more reliably? Can we make it work better? And can we also make it work with less components? And all those questions you can answer by filling and playing around with it. And this is what happens when you're designing something. And that's exactly what I've done. I've made some changes to the circuit and actually simplified parts of it. And I have actually drawn up a final schematic which we'll look at before the end of the video. But let's go through the changes that I've made. First off, that capacitor in the background there is now a 47 microfarad 60 volt as compared to a 100 microfarad 63 volt, and that takes the delay time for the relays to turn on from 6 seconds roughly down to 4 seconds roughly. That's a more acceptable delay. Over on the input side, I've got at least one channel with the correct 10 microfarad 50 volt bipolar capacitor as opposed to an electrolytic, and that'll become evident later as to why I've done that. You'll notice a jumper lead connected in mid-air there. That's actually connected to a 22k resistor going to the base of the second transistor, the PNP transistor in the circuit there, which you can't see because the alligator clip's in the way, but it's going to the base of that transistor. And that'll also become apparent as to what that's for shortly. And I've got a 5 watt 470 ohm dropper resistor for the relay driver, so it can actually drive more than one relay, because I had a 390 ohm, which is all I had at the time, connected there, and when I connected both relays in parallel, that resistor was getting red hot. At the moment it's warm, not overly hot, but we'll soon find out how hot that gets when I actually connect a second relay across the circuit. You'll notice two LEDs there. This one here just shows me that the circuit's got power. This one over here is the DC to detect, protect light, which comes on when there's a DC fault condition. That has also been modified, and that's been made simpler, and the two transistors that were driving that are totally gone. And we'll look at the schematic at the end, as I said, and you'll see why. So those are the major changes. I haven't really done anything else except change these two input transistors here from the BC549, I think I had in there, and 559 respectively, to 546 and 556 as in the final design. Now, if we grab a battery, and I'm going to make my life a little bit easier here. I'm going to connect the 9 volt battery up to the positive, the input lead, and I'm going to take this negative input lead here, just leave him floating, and just touch it to the battery. Now you may notice straight away nothing's happening. Okay, so now if we reverse the connections on the battery, now it's detecting negative DC, and the light goes back out. So how come it doesn't work in the positive direction? Well, it's pretty simple, because this battery is sitting at about 9.6 volt. And if we look at our original circuit plan, so here's our input. We're going through a 100k resistor, and in the positive direction we're going through this diode here. So we're going to also have a 0.6 of a volt drop here. That then goes into the base of this BC546 respectively. Now, in the reverse polarity direction, we're going through the 100k resistor, through this diode here in the cathode, and coming up through the emitter. Now, there is a 0.6 of a volt difference between the emitter base junction and the base junction alone. So if we take a multimeter, for instance, and we measure at this 100k resistor after the input, we can actually see what the voltage drop is on that 100k resistor. Now, you could use Ohm's law and a bit of math to calculate that, but in the real world it's a lot simpler and easier just to stick a meter on it. And we'll also stick a meter on the cathode of this diode, which is just basically the base of this transistor, and we can actually see what the voltage is. So first we'll just see what the actual battery voltage is at the moment. We're currently sitting at 9.06 volt. A fresh 9 volt battery not under load on a multimeter should be closer to 9.5. So it's a good indication that battery's starting to go flat. Alright, so I'll connect the positive of the multimeter across the other side of that 100k resistor at the input there, and we're not getting much. Now if I touch the negative of the battery to the ground of the circuit, absolutely jack shit happened. Yeah, right. Oh, that's because I'm on the wrong input. Might help if I connected the battery to the correct input. Okay, let's try that again. So according to the meter there, we've got 1.07 volt, and I just lost my battery. Now if I connect the battery up in the reverse direction where I know the protector will activate, we've still got 1.01 volt there. It's only a difference of about 0.05, about 50 millivolt or so. Okay, so I'll reconnect that back in the correct direction, we'll call it. So it's detecting positive DC. I'll move this probe from the resistor to the cathode of that diode, which goes to the base of the transistor, and I'll touch the negative to ground again. We've got roughly 0.603 and falling volt. It's not quite enough to turn the transistor on. They do say that it's supposed to be about 600 millivolt to turn a transistor on at the base. You're looking at more like 650 to 700 in the real world. Okay, so we reverse the direction of the input polarity. I'll move the positive probe to the anode of the other diode in that circuit, which goes to the emitter of the transistor, and we'll look at what the drop is there. So now I'll just connect my negative probe to the positive of the battery, and we've got about 0.54. Now you may be saying, well hang on, why is it not detecting one way and detecting the other, and yet the voltages are different? Well, the simplest answer is to measure what's going on at the collector of that transistor. So if I move my lead from the emitter in this case to the collector there. Okay, so I'm now connected to the collector of the first transistor, and we're going to measure what the voltage is, because we're measuring between the collector of the transistor and the positive rail. Because this is an NPN transistor, it's going to be switching negative. So I've got my battery hooked up the correct way. No, I haven't. I've got it hooked up in the negative direction. I've got my battery now hooked up in the positive going DC direction. we can see that the collector's voltage is only 0.5 of a volt, or not quite the 0.6 of a volt we need. Now I've just reversed the connections. We can see we're actually at 0.8 of a volt. There is actually a difference of roughly 0.2, 200 millivolts, and the reason is, and that's because of the voltage drop that's going to be experienced between the base emitter junction, which is about 1.2 volt. It takes 0.6 of a volt to turn the transistor on, and there's also going to be a 0.6 of a volt drop here on the emitter, because don't forget, a transistor is basically like two back-to-back diodes. In the case of an NPN, the two anodes are connected to form the base. So that's the reason why there is a difference between the positive going detection and the negative going detection. It's because of the base emitter junction voltage drop. And because we're going directly into the emitter for the negative detection, it's not going to experience such a large drop. Plus also the battery's going flat on the test battery, that 9 volt battery there. So I have put the input voltage requirement for at least, in the positive going direction, 9.5 volt, and in the negative going direction, 8.5 volt. So we'll ballpark the input sensitivity voltage, if you like, of plus minus 10 volt. Because if we look at the collector of the Q2, which is the BC556, and it's still going in the positive DC detection mode. Well, it's working now because, well, it's connected up backwards. So if we look at the positive going DC detection with the battery positive connected to the input and the negative connected to the ground, the transistor is not turning on because there's only 0.5 of a volt at its base. Reversing it around, we get roughly 0.6 of a volt out, which is all we need. I want to clarify something. In the previous part, someone asked, why did I get rid of that transistor, that PNP transistor that was connected to the emitter of the first NPN transistor? Because now it's not going to detect negative DC. Well, yes it will. As I already explained in the previous part, but I'll explain again, positive is coming through this diode into the base of this transistor. So that's our positive DC detection path. Negative is detected through this diode, through the cathode, into the emitter of this transistor. That's our negative DC path. This is between the positive voltage VCC line of the power supply and the earth. Don't forget, the earth is floating between the half potential of the total supply voltage between VCC and VEE respectively. So when, say, VEE is applied to the input, because this is a virtual earth, well, it just swings in the other direction. It's still going to detect negative, even though this is single-ended. However, if this was mounted on a power supply that didn't have a center tap, a 0 volt rail, and this ground was actually negative now, then yes, it wouldn't detect negative DC. But because this is in a bipolar power supply, and you'll see from the schematic that it's still going to detect negative DC because it's going through the emitter of this transistor, because this transistor is already biased on. So we're still going to get a current flow through the emitter collector junction when negative is applied to the emitter. So I hope that cleared that up. But even though this is the single supply version, it still needs to be on a bipolar power supply. Another point raised in the same comment was I was misinterpreted as saying that Class D amplifiers do not require speaker protectors. That's not what I said. I said that this speaker protector was mainly designed for Class B/AB amplifiers, and I wouldn't use it on a Class A because Class A's have an output capacitor and shouldn't have DC, but I never said anything about Class D. Class D do need speaker protectors, but they have to be treated a little bit differently. The design of the circuit has to be tailored to suit the Class D, because a Class D amplifier does indeed have a higher DC offset, we'll say, on the output than a Class A, B or Class B amplifier. So you connect this up to a Class D amplifier and it suddenly trips. Well, that's because there's already a DC offset on the output. As I said, the input DC offset input on this circuit is around plus minus 10 volt. So if the amplifier was putting out 1 volt, then it won't false trigger the circuit. But I didn't say that Class D amplifiers didn't require DC speaker protection. I just said that this is designed for Class B, Class AB amplifiers. So, anyway, I hope that cleared that up. I know that cleared that. Now, we're going to move on to some tests. What I'm going to do is I'm going to put the circuit under a stress test. That is, I'm going to connect the input to one of the supply rails. I'll leave the multimeter connected to the base, I think it is. No, the collector of the PNP transistor when it turns on and gives me 0.6 volt. And I'm going to connect it to the positive VCC line on the input, and I'm going to leave it sitting there for 10 minutes. Now, under normal conditions of an amplifier fault, normally it wouldn't be sitting in Protect for that long. If there was a problem and there was no sound output, most of us people with some intelligence would turn the amplifier off. But you always got to stress test the circuit to make sure it's not going to fry itself. So I'll take my input wire and I will find a convenient place to hook it to VCC without losing the connection, which I keep doing. So I've got to be careful here because ground's connected there also, even though it's not going anywhere. But I'll connect this across the relay driver. So we've got it in DC protect mode now. I'm going to leave it run for 10 minutes like that and see if anything smokes, blows up, whatever. And that resistor is getting quite warm actually. So if I wanted to run 2 relays, a 10 watt would probably be better. But anyway, I'm going to leave that for 10 minutes. And the reason why I changed that to a bipolar cap is because I'm going to do the same test again in 10 minutes time in the reverse direction. And because there's an electrolytic there, we will be reverse charging the poor 10 microfarad capacitor. And as I already proved in the last part, reverse charging a capacitor for a long period of time is not a good idea. Anyway, we'll come back in about 9 minutes and we'll see what has occurred. Okay, it's been almost a good 10 minutes now, and the collector of the second transistor, the PNP transistor, is still sitting at a voltage output of, well, in this case minus, that's the leads around the wrong way, but at 0.68 of a volt. That's after the 100k resistor respectively. So now if I remove the DC fault, circuit resets. So nothing untoward has happened to the circuit. So what I'll do now is I will connect it to the negative of the power supply to give us a negative DC input voltage, being very careful not to bring that into contact with anything touching this breadboard chassis here, because that's metal and it will short it out. So make sure I connect it across the correct input, which is that one there. There we go. We're detecting negative now. Meter is saying 0.68, the same as it was in the other direction. So now we'll just leave that to cook, if you like, for another 10 minutes or so. And we'll come back and see if it resets. Okay, it's been about 5-6 minutes. I know I said about 10, but 30 seconds is long enough to destroy a circuit, trust me. So let's remove the negative DC. Circuit resets just fine. So it hasn't killed anything, and let's face it, the reason why I'm doing a stress test at the full voltage rails here is because in an amplifier fault condition, when an output transistor shorts, and it can be in a discrete amplifier, it can be in a chip amplifier, it makes absolutely no difference. The output transistor is usually going to short, which means one of the power supply rails, either the positive or the negative, is going to be present at the output because of that short circuit. So the DC detector is going to be presented at least 1/2 of the voltage rail to it. So we test the circuit at that potential. So if the supply voltage was plus 35 volt, we would connect plus 35 volt, or thereabouts. It'd be about one, maybe half a volt difference, but 35 volt to the input. See if anything destroys itself. So far, it hasn't. So I know this circuit is pretty rugged and will handle the supply voltages, reverse and normal direction just fine. As for this 22k resistor that's floating in mid-air here with this jumper lead connected to it, it was a 10k, but I've changed it now to 22 because, well, I couldn't read my own schematic. What is it for? Well, if we take this to ground, this resistor, we notice that it goes into protect mode. If you could see the LED is now lit. So what would you use it for? Thermal overload. What you would do is you would connect a thermal switch, one that's in the normally open style, not normally closed, of whatever temperature you want to activate that switch at. They range from 60 to, I think it's 160 volt. 106. They range from 60 to 160 degrees Celsius, so you choose the appropriate one. 160 degrees is very, very close to the safe operating curve of a transistor anyway. But we would monitor the temperature of the heatsink with that switch, and once it reached that threshold of whatever that switch is temperature sensitive to, it would activate the circuit. So it would also protect not the speakers but mainly the amplifier from thermal overload. So if the heatsink was getting too hot, it would disconnect the speakers, thereby disconnecting the load off of the amplifier, therefore giving the amplifier's output stage a chance to cool down. And once it's cooled down enough, which could take a fairly long time depending on the heatsink used, if it's a really bad choice of heatsink, it may take a longer time to dissipate the heat than a heatsink that should have probably been used with it. And when it does, fault condition goes away, relay re-engages, reconnecting the load. So basically in this design I have thought of everything, or almost everything. Now this is all just testing it from a DC power supply. What about from an actual AC transformer as if it was in a power supply? Well, I can build up a bridge rectifier and filter capacitor stage here and connect a transformer. I've got an 18018 there in that test amp, which would be give me just enough voltage, about 24 after smoothing, to do the tests with and see if anything does fry. It shouldn't, but you never know. So I'll do that next before we look at the schematic. But I don't know if I mentioned I changed the loss of AC detection circuit to something a little different from this. As previously mentioned, this comes from the transformer secondary, and it's a half wave rectification here. And it's looking at the negative going cycle of the AC waveform. That generally wouldn't be a problem, but if we look up here, we've got another diode with the cathode connected to this 15k resistor, and the anode of this one's connected to this 15k resistor. These two are joined together in the center of the base of that transistor. So this is actually a voltage divider. The thing I'm concerned about is because this diode goes off to the VCC line, so you can only pass positive in that direction, and it can only pass negative in that direction. My concern is, because we're rectifying the negative going cycle here, it's got the propensity, because of this voltage divider network here, to inject noise onto the VCC line from this side. And yeah, I didn't like that. This circuit, I cannot remember if I did or did not test it before on a transformer. I don't remember. Or whether I just pinched it off the internet from somewhere without fully testing it. I don't know. I can't remember. So I've dropped that and I've gone with a more conventional approach, which will be explained in the schematic at the end here. And basically I've used Rod Elliott's loss of AC detection circuit from the same project, which is linked in the description, because I trust that to work flawlessly than I do trust this. It probably would work okay, but the last thing you want to do is have noise and hum on the power supply line unnecessarily. Even though that's going to the filter caps, it will probably filter it out. But yeah, that's just bad design, because it's allowing the negative going raw AC, if you like, signal to go back onto the VCC line, which is not really good. There was also a few 10 ohm resistors between collectors and bases of transistors that I got rid of and directly wired because they weren't necessary anymore. That's what I meant when I said finding out how many components the circuit will work without. So we're keeping the BOM, the bill of material, down, but still making the circuit work effectively. So I've saved probably 3 transistors, 3 resistors, a couple of capacitors, and 2 diodes, I think it was. So that also makes it a lot easier when laying out a PCB. You don't have shitloads of components to deal with. So the next thing is I'll build up the rectifier circuit over here for the mains and hook it up to a suitable transformer, and we'll test the circuit again and see if it still operates or it goes bang. If it goes bang, hopefully I capture it on video. See you in the next shot. Okay, I got the bridge rectifier and filtration capacitors hooked up. These are two 4700 microfarad 50 volt caps, and these are just 1N4007 diodes connected in the standard bridge rectifier configuration. I've got that hooked up across the secondary of that 18018 volt transformer, and I've just got fly leads connected to the secondary, but I've got to be very careful that it doesn't come into contact with the chassis. It's unplugged currently. I've got the multimeter set on the DC voltage range across the positive and the negative voltage rails of those capacitors. And I've checked and double checked and triple checked that everything's wired correctly here, so nothing should go bang. I'm just going to sort out this power cord, which is crap. Very stiff. I'll plug him in. Alright, turn on the power switch. We've got 54 thereabouts volts across the plus minus voltage rails, which if you divide that by 2, that's about 27 volt thereabouts, which is what the DC power supply was set to, which is about 27.2. So the circuit should still work the same. If I connect that to the 0 volt rail between the positive and the 0, we get 27, so that's fine. Carefully disconnect that. Turn him off for now. Let's see how long it takes for it to discharge. Quite a fair while. Slowly bleeding off. So now I need to connect that to the DC rails of the circuit plus the AC. Let's go. Okay, I've connected the positive VCC rail up to the positive of the capacitors. I've connected the negative or ground to the 0 volt. The loss of AC detector, which is now using a full wave rectifier instead of a half wave, is connected to both AC inputs from the secondary. Everything else is not shorted on the chassis. Haven't turned it on yet. The meter is connected across the relay coil, well, across the relay driver anyway. Well, that wouldn't be correct, so I'll connect that to actually across the relay. There we go. And I haven't powered the circuit up yet, so this is the first time I've powered this on AC from a transformer. So if it goes bang, it's going to be captured on video. Let's turn it on. And nothing went bang. And now we've actually only got about 9 volt across the relay coil. So that resistor is a little bit high in value. Now I would touch the transistor that's responsible for the loss of AC detector with my finger, but I don't really want to come into contact with AC. Nothing's happened to it and I can't smell anything, so everything is working fine so far. So now what I should probably do is connect positive input. I don't know why I keep calling it that. Let's connect the sense input for the DC detector to the positive rail, see if anything goes bang. No, it doesn't. So we move around the other side and I'll just touch it to the negative side now. Nothing untoward happened. And reset. Brilliante. Okay. So I'm going to leave that run on the transformer for a while, see if the circuit still operates after 10 minutes. If it does, it should be fine, and the design is now complete. Okay, the circuit's been running for a good 10-15 minutes on the AC transformer, and this LED is actually connected via a drop ring resistor to the 2 cathodes of that 4-wave rectifier there, and it's unsmooth, there's no filter cap there, but that LED is not flickering or anything, and that will also instantly go off with the power as soon as the power switch is turned off. So I'm going to leave that there as a power indicator that will instantly turn off when the power switch is turned off, which is better than having, say, one of those Chinese power switches like I used in the other amplifier. You turn it off and it takes a while for the LED to extinguish because it's coming off the filter caps. It would have been nice if they had internally switched the LED as well, but they didn't. But that's another way around it. Having raw, unfiltered AC going through that LED isn't going to affect it much. Let's face it, it's a diode. It's still a rectifier. Anyhow, if we turn off the power switch and look at the drive for the relays, instant off. So that loss of AC detector is doing what it should do. Turn it off, LED goes out. So before we look at the schematic, one final DC check, which is positive, it's fine. Negative, it's fine. So the circuit's working, I can put the breadboard away and now concentrate on making up the PCB for it, like going through and laying it out, which will be a topic of another video. But to end this video, I did want to achieve more today than I did, but I can't really be bothered now. I'm going to put this away and we're going to take a look at my enormous penis. No, we're going to take a look at the schematic. I'm pretty sure what I should really be doing, and that's what I was going to do, is connect another relay across the driver and see how hot that 5-watt resistor actually does get. So what might be a good idea is to disconnect the multimeter from the relay. I need my temperature probe, wherever the fuck that is. Alright, so I've got the temperature probe hooked up to the multimeter, and I'm just going to touch the probe onto the resistor. And it looks like it's sitting at around 30 degrees Celsius, which is fine. So I'll connect up my other relay in parallel with the first. So that's another relay connected. That means there's going to be double the current draw. Now, I calculated the wattage of this resistor based on the current draw of one relay, which was 0.047 amps, which is 47 mA. You times that by 2, that's 94 mA. So if you then multiply the voltage of 12 by 0.094, you get 1.12 watt. So a 1 watt resistor as the dropping resistor would have been under. 5 watt is overkill, but is guaranteed not to fry itself. Now, touching that resistor, and that's been connected for a good minute whilst I was talking, because it's drawing more current, that would have heated up a lot quicker, but it's barely even warmer. It's probably now at around about 40 degrees Celsius. So I'll touch my temperature probe to the resistor again. Oh look, we're at 32, 33. It barely made a difference. All of about 3 degrees Celsius. After a long period of time that may get to, I don't know, 40. But I know that 2 relays across that driver circuit is not going to kill it. The driver transistors themselves, I can't actually feel the temperature of them, but I can measure the temperature by touching my probe to it. Barely 20 degrees Celsius. So those transistors are fine. I believe that comes off of that one. Yeah. So if I touch the other one, meter's not moving. So I know that those transistors are not getting hot. That resistor is mildly warm, but is rated for the job. So now let's take a look at the schematic. And here is the schematic drawn out. Now this is designed as a complete power supply unit, as we can clearly see. I've designed it to run on plus minus 35 volt. I've set the maximum that you should probably run this at in the current configuration, especially with these BC549 transistors here as the relay driver, to no more than plus minus 40. You could theoretically run this higher, up to probably plus minus 55, but I would change these drivers to BC546s. So let's go through the circuit here and have a look. First we'll look at the comments. As I said, it's designed for plus minus 35, maximum supply voltage of plus minus 40, already described. R16, which is the dropper resistor for the relay driver, is calculated by R equals plus VCC, which is the positive voltage rail, minus the voltage of the relay coil. Now in this case it's 12. You could use a 24 volt relay coil if you like, it makes no difference. You just change that to 24, divided by the current of the relay coil. Let's see, by I, where I is the current of the relay coil. Now, then once you've worked out the current of the relay coil, because there's 2 of them, as I said, you're then going to have to use the power law to calculate the wattage of the resistor required. In this case it was 1.12 watt. It requires a 5 watt 470 ohm resistor at 35 volt plus minus. It's also got part designed by Rod Elliott from Elliott Sound Products. I'm giving him credit because the DC detector and the loss of AC detection circuit are his. So anyway, we've got over here, we've got the left input, the right input and the sub input all going into these filter networks as it was on the whiteboard. 22k resistor is to bleed this 10 microfarad capacitor off of its charge. The positive going cycle is going to be rectified and detected by these three diodes here, which go into the base of the transistor Q1 over here. The negative going cycle is going to be rectified by these three diodes here and going into the emitter of this transistor here, as previously discussed. And the base of the transistor is biased on to the ground point via this diode down here. So when Q1 conducts, it'll turn Q2 on, which allows current flow from the emitter to the collector. This will illuminate the protect LED. See, now that I've moved the protect LED directly to here, we don't need to see the protect LED on whilst it's charging up the RC delay, which is over here off screen, before the relay is engaged. That's not important. All we need is a visual indication that there is a fault, which will be probably most likely permanent, so the LED will be on all the time. If the fault goes away, the LED just extinguishes automatically, instantly, and the fault's gone. That's all it is, it's fault indication. And over this side we see this 22k resistor I was talking about, which can be connected to ground. That goes to the base of Q2 here, and that's for, as previously described, the temperature sensor, which is going to be a temperature sensitive switch mounted to the heatsink. So if I used a 60 degree normally open temperature switch, once the heatsink reached 60 degrees Celsius, the switch would close, which would then turn the base of this transistor on, again allowing current to flow through the emitter collector junction, turning on the protect LED, I keep saying LED, sorry, and then effectively turning the circuit into protect mode. And that's what you want. You want DC detection plus thermal overload detection. Don't have to use it, it's not important. So once this transistor turns on and the protect LED is on, it's going to turn this transistor Q3 on. And once that turns on, it needs only about 0.6 of a volt there to turn it on, and that's roughly what I measure at the off point, is 0.6 of a volt. It's going to allow the earth connection, or the 0 volt rail, to flow current. It's going to allow current flow through the emitter, up through the collector, effectively stealing the base current from the relay driver over here. So here's our Darlington relay driver over here, which is connected via the positive rail here, which is connected to VCC, through the 100k resistor and the 47 microfarad RC network here. And that diode there, as previously mentioned in the last video, is to provide a quick discharge path for the capacitor when the power is removed. Now, if we look at this relay driver Darlington configuration here, here's R16, which was previously talked about. You notice this mute input here, which goes to earth. Now, this means that there should be an always normally closed switch connected here, otherwise there's no connection to earth, there's no current flow. What this could be used for is if you've got, say, a separate headphone amplifier in the amplifier that it's connected to. As soon as you plug in a pair of headphones, the switch will open, instantly disconnecting the relays. So the speakers effectively turn off and now the headphones are on. That was the whole entire idea behind that. Now on my PCB, if I wasn't going to use that function, even though it's still there, I would just simply put a link wire or a solder bridge or something across the two pins there to connect it to earth so it's constantly on. Or install a header, because they have the same pitch as the connector that I'm going to be using in the final design, and just put a jumper over it, whichever way. And the collectors of the Darlington pair go to these two relays in parallel. One's a DP-DT and one's an SP-DT. And we'll notice that the normally closed positions of each of these switches are connected to the ground up here. And the normally open are connected to the LN, RN and SN respectively, and these connect to the same points on the left hand side of the circuit over here. I've just basically had two separate inputs there because it's a lot easier drawing the schematic. It looks a lot cleaner than having lines going all over the place just to join these two up. Effectively, these 3 points here are connected to these 3 points here physically, and the outputs are formed on each of the common points of each relay. So we've got the left out, the right out, and the subwoofer out. The loss of AC circuit is down in the bottom here, and it's based on this transistor Q4, which is the BC549. We've got a full wave rectifier here. Either end of these anodes is connected to one side of the secondary winding with relation to the center tap, which is the earth point. So that forms a full wave rectifier. The power LED is just taken off of the cathodes and taken to earth. That's fine. We saw on the breadboard there that was working fine. Now, basically, we take the raw, rectified, unsmoothed secondary voltage, and because it's pulsing at 60 cycles per second, and we're getting the full ripple, not half wave ripple, it's basically pulsing this transistor on at around about 60 cycles per second. That's enough to keep this transistor conducting, allowing current flow up through from the emitter through to the collector, which is causing this capacity here, which is a 1 microfarad, to be in the discharge state, because the positive of that capacitor connects through this 100k resistor up to the positive rail here, the VCC line. So as long as the AC is connected to these two diodes and it's pulsing this transistor and keeping it turned on, this capacitor will remain discharged, which is then fed through this diode into the off point, which is the base of Q3 here. Now, in a DC fault condition, remember Q2 up here, the PNP transistor will turn on, turning this transistor on. And when the AC disappears and this transistor stops conducting, there's no current flow from the emitter through to collector anymore. This 100k resistor and this 1 microfarad capacitor respectively form now an RC circuit, time constant. So then that will charge this capacitor. That will allow a positive flow through the anode of this diode, biasing this transistor on. And what happens when this transistor biases on? Just like in the DC fault condition or over temp, it steals the base current from the driver circuit, the relays drop out. And that is the whole entire important part of the circuit. Up here is just the DC side of the supply, giving us the high power rails and the plus minus 15 rails for a preamp, using an LM3170 and a 3370 respectively, with a trim pot at the adjust point. So you can actually make it higher than 15 volt if you want. You can make it, you know, up to 18 volt depending on what op amps you're using, just to give the preamp a little bit more headroom, just so to speak. But that is the entire circuit. I drew this entire circuit out in a free program which is licensed under the GNU licensing scheme called KiCad, or KiCad, K-I-C-A-D. And this was version 4.0.7. I'll put a link in the description to that. I haven't tried the PCB layout part of it yet, how intuitive that is. For a free program, it does draw up a nice schematic. My gripes are all the pin numbers around transistors, which are unnecessary. Also pin numbers around relays, also unnecessary. The only pin numbers you should really see are on IC devices like regulators, op amps, linear ICs and digital ICs, etc. You don't need them on transistors. I suppose in a way it does give you an indication on the schematic going 1, 2, 3 where the collector pin is, the base pin and the emitter pin are respectively. So in this instance, BC549, pin 1 is the collector, which is on the left. So, because it goes from left to right. That's the only gripe I've got about it. Plus, when you're connecting up your wire lines to components, if you have to drag something across, like move it, well, it doesn't increase the length of this line, it just moves it, and so it disconnects it from where it was connected, which is thoroughly annoying. But that's the only gripe. The learning curve of it is pretty simple. It's not that hard to use. It is pretty intuitive. But if you want a free CAD program, KiCad is proving to be pretty good. It's about 700 megabytes to download. So the component library is pretty extensive, but as I haven't tried the PCB layout part of the program yet, I can't give a full review on it. I'm still debating whether or not to lay out the PCB using KiCad or go back to my paid program of Proteus 7.5. I don't know. I like Proteus 7.5 PCB layout. I don't like the schematic layout part of that program for various different reasons. But okay, I've got a free program that I'm using to draw the schematic, and I've got a paid program to do the PCB. Who cares? But the reason why I say it's a good schematic layout program is because, well, it actually draws transistors like they're supposed to look like on a schematic. The transistor symbol with the circle around it. Proteus is just the transistor symbol, or basically the two diode symbols, but no circle. And yeah, it's alright, but it just doesn't look like a professional schematic. Plus, half the components are larger than others. Like the transistor is like bigger than the resistor in physical size, and voltage regulators are like 3 times the size of a transistor. So it ends up taking up more space on the schematic layout because component sizes are all over the place. At least this looks reasonably, you know, no component is oversized for no reason. Well, except maybe the relays could have been made smaller. Anyway, that's beside the point. That's the entire schematic. That'll be available as a PDF file, link in the description, plus a link in the description to KiCad. Yeah, so that's the entire design process for this speaker protector / PSU done. All it needs now is a circuit board, so that's the next thing to do, is to design the PCB and make the PCB, and yeah, that'll be the final part of this series, I think. Maximum voltage, as I said, should be no more than plus minus 40. You could probably get away with plus minus 55 if you change the Q5 and Q6 to BC546s, as I said. As for minimum voltage, well, if you're using 24 volt relays, I wouldn't go any lower than 18018. If you're using 12 volt relays, I wouldn't go any lower than 15015. Haven't tested it, I don't have those voltages obviously on hand to verify that. But yeah, I reckon the minimum would be 15015. Anyway, I'm the Astro 30. I hope you enjoyed this video. Please remember to rate, comment and subscribe below, and you can always follow me on Facebook and Twitter. The links are in the description as usual. Anyway, this is the Astro 30 saying see ya. I can't talk anymore, and I'll see you in the next video. Bye for now.